Welcome back again. In the previous videos, I covered decision function attribution for gapped-Kamer SVMs. In this video, I'm going to describe how hypothetical importance scores are generated for SVMs with weighted gapped Kamer kernels and SVMs with weighted gapped Kamer RBF kernels. So first, what exactly are hypothetical importance scores? As you may have seen in the past videos, when decision function attribution was performed using integrated gradients, that essentially established an importance score for the specific base at each position in the input sequence. When these importance scores are used for motif discovery in genomic sequences, it is useful to also know the hypothetical importance scores of other bases at each position in the input sequence. For example, here, we show an input sequence in which the size of each base in the sequence represents its relative importance in contributing to the decision function's value for that sequence. The G at position 5 in the sequence has an importance of 0.3. Now, if we instead had a C at that position, would it have been more or less important? The predicted importance for C at that position would be its hypothetical importance score at that position. In this slide, I'll cover hypothetical importance scores for weighted gapped kernel SVMs. So the hypothetical importance score for any base at a position is calculated in much the same way as the contribution for the actual base that is present at that position. So let WGKM SVM HIG SX I, B star denote the hypothetical contribution that base B would have if present at position I in sequence SX to the SVM decision function. Much like in previous cases, it is simply equal to the summation of the weighted contributions for the same base and position from each support vector. The contribution from a specific support vector is given by the term HCW GKM SX SZJ I, B star. In the next slide, I'll explain this term in more detail. The computation shown here for HCW GKM is very similar to the computation of CW GKM, which was the contribution to the decision function from the actual base occurring at position I. This was covered in detail in the video on decision function attribution, and it might help to review that first if you have not already seen it. So here, the only real difference from the CW-GKM calculation is that when a pair of Elmers is considered, then the attribution must be done for the hypothetical base B, not the actual base that was considered in the CW-GKM calculation. Again, this is best illustrated by an example. So, in this example, we have the input sequence S1 and the support vector SZ. We are using Elmers of size L equals 4, non-gap positions K equals 2, and the position of interest I equals 2. The base we actually have at I equals 2 is G, but the base we want to know the hypothetical importance scores of is T. We again consider the same three cases we considered for the CW-GKM calculation, and show how that calculation is to be modified for hypothetical importance score calculation. So in this first case, the original number of mismatches was M equals 1, and the pair of Elmers, U2 from S1 and U1 from SZ, did have a contribution to the position of interest for the actual base G. But since now there is a T instead of a G, there is a mismatch, and even though there is a contribution from this pair of Elmers, it cannot be attributed to the T. So the hypothetical contribution here is 0. In the second case, there was a mismatch at the position of interest, so there was no contribution from this position for this pair of Elmers. But the hypothetical base T at the position of interest now creates a match. So since the original set of mismatches was 2, we reduce that by 1 from 2 to 1 and calculate the attribution to the hypothetical base T as the total attribution, shown here. H of 2 minus 1 is divided by the number of matching positions, which is 3. This gives a hypothetical contribution of 1 due to this pair of Elmers. In the third case, the number of mismatches was already 3, and there was no contribution at the position of interest because even though the actual base was matched in both Elmers, the number of mismatches was too high. With a hypothetical base T at the position of interest, even the one match is lost, so clearly there is no change, and the hypothetical contribution remains the same as the original contribution, which is 0. So at this point, how to calculate the hypothetical contribution for each base at any given position of an input sequence to the decision function for the WGKM kernel should be clear. In this slide, I'll cover hypothetical importance scores for WGKM RBF kernel SVMs. As before, the hypothetical importance score for a base at a position for the WGKM RBF kernel is calculated in much the same way as the contribution for the actual base at that position. And the corresponding formulas are as expected. So here, WGKM RBF SVM HIGSXI, B is the hypothetical contribution that base B would have, if present, at position I in sequence SX to the decision function. Exactly as in the previous case, it is equal to the summation of the weighted contributions for the same base and position from each support vector. And this contribution from each support vector is given by HCW GKM RBF SX, SZJ I, B. And very similar to the corresponding formula for the actual contribution, HCW GKM RBF SX, SZJ I, B, shown here, can be thought of as distributing the difference from baseline of the WGKM kernel function in proportion to HCW GKM I, B SX, SZ, divided by KWGKM SX, SZ, which is the fractional hypothetical contribution to position I of the WGKM kernel output. And that completes the description of hypothetical importance scores. Thanks for watching.